Hello, my name is Joshua Meggs. I'm a student in MA 722XA, Non-Euclidean Geometry at Emporia State University, and this is my proof of an equivalence to Euclid's fifth. The statement I'm going to be proving that is equivalent to Euclid's fifth is that the sum of the interior angles of an n-sided convex polygon with n being greater than or equal to 3 is found by taking n minus 2, that quantity multiplied by 180 degrees. So the first direction that I'm going to show is that using the basis E plus Euclid's fifth, we can prove that the sum of the interior angles of an n-sided polygon with n being at least 3 is given by n minus 2 multiplied by 180 degrees. We're going to do this proof by induction. Our base case, we're going to consider n being equal to 3, which is a triangle. Plugging that into our formula, we get that 3 minus 2 multiplied by 180 degrees would be equal to 1 multiplied by 180 degrees, which is in fact the angle sum of a triangle. So the statement holds for the base case. Our inductive hypothesis is that we're going to then assume that the claim is true for the kth case, that is, that the sum of the interior angles of a k-sided polygon is in fact k minus 2 multiplied by 180 degrees. So let's consider a polygon with k plus 1 sides as pictured with k plus 1 vertices as labeled. By postulate 1, let's connect vertices a1 and a sub k as shown. This creates triangle a sub 1, a sub k plus 1 with angles as labeled. By the base case, we know that the angle sum of this triangle is given by angle 1 plus angle 4 plus angle a sub k plus 1 equal to 180 degrees. And we'll call that equation 1. Also, we have that the angle sum of the polygon, a sub 1, a sub 2, a sub 3, all the way up to a sub k minus 1, a sub k, is equal to k minus 2 multiplied by 180 degrees by the inductive hypothesis. Thus, angle 2 plus angle a sub 2 plus angle a sub 3 plus angle a sub k minus 1 plus angle 3 would have to be equal to k minus 2 multiplied by 180 degrees. And we'll call that equation 2. So by axiom 2, we'll now add equations 1 and 2 to get the following equation, which states that angle 1, which as a reminder is this angle right here, plus angle 2 plus angle a sub 2 plus angle a sub 3 plus the rest of the consecutive angles all the way up to angle a sub k minus 1 plus angle 3 plus angle 4 plus angle a sub k plus 1 would have to be equal to the angle sum k minus 2 multiplied by 180 degrees, which was for our larger polygon, plus 180 degrees, which would be for the triangle that we partitioned off. We do also know that angle 1 plus angle 2 add up to be angle a sub 1, and angle 3 plus angle 4 has to add up to be a sub k. So by substitution with axiom 1, we can change our equation to now being angle a sub 1 plus angle a sub 2 plus angle a sub 3 plus the rest of our consecutive angles up through angle a sub k minus 1 plus angle a sub k plus angle a sub k plus 1 being equal to k minus 2 multiplied by 180 degrees plus 180 degrees. On the right side then, we'll go ahead and factor out that 180 degrees rather than doing it the conventional way and moving the 180 to the left side. We'll leave the 180 on the right side of the expression. Then using the associative property, we'll regroup what we have in the parentheses as parentheses k plus 1, that quantity minus 2, which is exactly the k plus 1th case. Thus, the inductive hypothesis holds for that k plus 1th case, and therefore it holds for all cases. So now, going the other direction, we're now going to use the basis E plus the fact that the sum of the interior angles of an n-sided polygon with n being greater than or equal to 3 being equal to n minus 2 multiplied by 180 degrees to show Euclid's fifth is true. So we're going to start by selecting 3 arbitrary non-collinear points, and we're going to label those A, B, and C as shown. By postulate 1, we'll then construct the line segments AB, AC, and BC, creating the triangle ABC with angles 1, 2, and 3 as shown. By the claim statement, we know that the angle sum of this triangle must be 3 minus 2 multiplied by 180 degrees, which is 180 degrees. Thus, angle 1 plus angle 2 plus angle 3 would have to add up to be 180 degrees. By postulate 2, we'll now extend AB in both directions. Let's go ahead and label this line as L with angle 6 as shown. By proposition 23, we'll then construct angle 4 on BC such that angle 4 is equal to angle 2 as shown. By postulate 2, we're then going to extend this new line containing C in both directions. We're going to label this line M with angle 5 as shown. By proposition 27, since we have angle 2 and angle 4 as congruent alternate interior angles, we know that lines L and M must be parallel. So then by proposition 13, we also can say that angle 3 plus angle 4 plus angle 5 would have to add up to be 180 degrees. And then by axiom 1, then we can set that equation, equation 2, equal to our previous equation 1 for the angle sum of our triangle to say that angle 1 plus angle 2 plus angle 3 is equal to angle 3 plus angle 4 plus angle 5. Then by axiom 3, we can subtract angle 3 from each side of our equation to get that angle 1 plus angle 2 is equal to angle 4 plus angle 5. From a previous notion, we already knew that angle 2 and angle 4 were congruent by construction. Therefore, we can replace angle 4 with angle 2 by axiom 1. Then by axiom 3, once again, we can subtract angle 2 from each side to get that angle 1 is congruent to angle 5. By proposition 13, we also know that angle 1 and angle 6 add up to be 180 degrees. And thus, by substitution with axiom 1, we now know that angle 6 plus angle 5 would have to add to be 180 degrees. Thus, lines L and M are parallel, with interior angles on the same side of a transversal AC being equal to 2 right angles. Therefore, Euclid's fifth holds. Thank you very much.